mod physics in iron-based superconductors.
Okay, thank you, Lara. I'd like also to thank the organizers for putting together such a beautiful meeting, for putting together these communities to share ideas and thoughts, even though, of course, the scheduling for me is not perfect, but that's just a minor point on the scale of the conference. So let me also take the opportunity to waste one precious minute for advertisement. Our conference that I'm organizing in Trieste next fall, also together with Sebastiano Pilati and Stefano Giorgini, who are in the audience here, and other guys. So, okay, this is what you can just, if you wish to take care of this. The idea is precisely similar to this one in putting together communities, even though, say, the multi-aspect is not so stressed here, but still a lot of things inside. So this is even the crisis period, conference fees probably appreciated. So let me go to the talk. First, I will thank the co-workers. So this is essentially what I will talk is in these two papers. And the main characters are two young colleagues. One is Gianluca Giovannetti, who is a non-permanent researcher hired thanks to the European Union. And the other is Luca De Medici, who is now in SRF in Grenoble. He's a guy that I've seen grown up in the years, and excellent theorist. And I also would like to thank these guys who are co-authors of one of the papers, and Marcus Eichhorn, Giorgio San Giovanni, and Alessandro Toschi for an aspect that we are investigating right now, even though I'm not sure I will cover them. So, what I'm going to talk about, I mean, I'm not actually talking too much about multi-whatever superconductivity, condensate bands, orbitals. I would rather make a little step back onto something which is like, say, the ground on which superconductivity appears in, we believe, most of these materials. So, I mean, there is one, say, bottom line to describe the way you should look, or you may look at the phase diagram of high-density superconductors of the cuprates, which is that the story, everything boils down to doping a Mott insulator. So when you, so this is, I mean, it's sideways phase diagram, but just for graphical reasons, essentially, so you go from this antiferromagnetic Mott state, you dope it, and you get into the famous pseudo-gap region, then you have the superconductor, I mean, and finally you get something which looks like a normal metal in the overdoped region. This is, of course, something that it's very well known, and it sort of mirrors, say, a decrease of the role of electron-electron correlations, which are the thing that makes the Mott state localized, as Sir Mott discovered, and they are, say, decreasing their impact as we go away from this Mott state. So, this is for the cuprates, and essentially people have learned to believe this story. So now let's come to the iron-based superconductors. Of course, I don't need to make an introduction because several speakers did it in some details. We have a bunch of materials which all share these iron something layers, mainly pnictogen but also chalcogen. And so they share some structural chemical analogy with the cuprates, and somehow they share a phase diagram that, at least at first glance, may look similar to that of the cuprates. We have some magnetic state, which here is a metallic spin density wave, which turns into a superconductor when we dope. So, I mean, as we've learned from previous speakers, different stories happen in the different subfamilies of this family, but still there is this overall thing. So, one natural question, which was one of the first that came in people's mind after this discovery, is whether we should see these materials as understand these materials as what happens by doping a metallic spin density wave, as opposed to doping a Mott insulator, an antiferromagnetic Mott insulator, as it happens for the cuprates. Which, in the end of the day, means whether, now I turn the diagram in the more ordinary fashion, whether we should compare this diagram with the cuprates with those diagrams. So, essentially, my answer will be a yes and no, and there will be somehow a twist before the end, so wait for the twist. Let's say that if we accomplish such task, we can sort of hope, and that's sort of the underlying idea of this European grant that I have, that we can unify. Whatever. Okay, it's just that the disk is almost full, and the Mac works even when I'm not using it. So essentially to unify the diagrams of many materials. The two that I mentioned here, I mentioned a less known member of the family, which are the alkali doped fluorides, and I can also put, for example, the heavy fermion materials. So we may really hope that superconductivity in non-standard material as a sort of universal way to understand. And that superconductivity sort of appears when we are at some ideal distance from this insulating or bad metallic state. There is an optimally bad metal, which also, this is sort of link that I'm not going to discuss here, that the general picture may be of a correlation-driven BCS to BEC crossover, going from the, say, overdoped side to the underdoped side. Okay, let's go back to the iron-based materials and see what I can tell you about them in this context. So, essentially, we would like to think about what is similar and what is different between the families of material in the light of correlations. So, there are some aspects that sort of point towards the idea that these materials, the iron-based superconductors, are still correlated. Of course, there is many people think that there is a magnetic or anyway an electronic mechanism. Say the odds for a phononic mechanism are moderately low. Then everything anyway happens doping a magnetic state. So this magnetic state is likely to play some role. And that this metallic state is not a good metal. You can see it in many ways, the scattering rate that Sergei was mentioning about before, or even simply the normalization of the bands by a factor 3. These are all things that point towards something where the metal, whatever it is not the ideal metal of the standard superconductors. On the other hand, there are aspects that point towards a different direction. So first of all, there's no multi-insulator in the parent compounds. So the metallic compound is anyway metallic. So one of the other things is that people typically say that there are no Haber bands, which are the fingerprints of the Haber physics. Even though I'm starting to put a question mark whether it's wrong, as Sergei is showing us in this ARPS data, that at least in some members of the family, the Haber bands tend to appear, even though they are not pronounced as in the cuprates they are there. And the other maybe wrong thing is that there is a widespread feeling that density functional theory is not too bad. It describes the band structure quite well, and still, once again, I have to invoke Sergei was showing that at least the cartoon that came out from first DFT calculation doesn't seem to be the right cartoon to play with to understand what's really measured in these materials. And then there is something that I will not comment too much about. There is a, say, well, we could quote some puzzles about the magnetic moment. We have some, say, conflicting evidences about small and large magnetic moments, which might have to do with the dynamics of them, and so on and so forth. Yet, let's say the bottom line is that there is no very strong evidence for clear, well-formed magnetic moments, which would be the one of the main fingerprints of strong correlations. Of course, there is one simple way out of this. Just say that, okay, it's simply that we are in the middle. These materials are intermediately correlated, and they live in a world, say, somehow in the middle between high DC superconductors and low temperature superconductors. Actually, sorry, I'm not able to use this thing. Our answer will actually be that you should rather think that they are both weakly and strongly correlated in a sense that I will discuss in the following. Okay, so let's say that the community sort of splits between people that think of correlations are very important and people that think that correlations are not so important. There is definitely one thing that the community, everyone agrees on, and of course that fits very well in this conference, is the multi-orbital nature of the electronic states in these materials. So all the 5D orbitals play a role. They are close to the Fermi level, and they sort of play some role in everything that we see in the experiments. So a multi-orbital description is necessary. Let me mention that the count of the electrons in these materials would be, if you take a fully, let's say, pure description in terms of iron d orbitals, to have 6 electrons on the 5 orbitals of iron. So it's an integer number, but it's not half-filling. It's not the same number of electrons as the number of orbitals. This thing brings about at least 2 important effects. One is the role of the Hund's exchange. If I want to build some theoretical description of what happens, I have a multi-orbital model. If I am reasonably close to some atomic physics, the local Hund's exchange will play a role. And the other is that there is at least the chance that the orbitals will behave differently from one another, which is what I call here orbital selectivity. So the behavior is not the same for all the orbitals, something that also Sergei once again was hinting at some point during his talk. Oops, I hate this thing. What did I do? So, Kuhn's rule, this is something that I just remind briefly. So, what we will do essentially is to try to build a microscopic understanding of these materials. So we want to put the interactions. And what we have is that besides the Hubbard U that Frank Marsilio has introduced this morning, it's just say, essentially the short-range part of the Coulomb repulsion, we need to introduce the Hund's coupling, which is what gives rise to the Hund's rules in atoms. So it's something that wants to, first of all, maximize the total spin of electrons sitting on one atom, and then, as a second prescription, wants to maximize the total angular moment on the same atom. The third one it's not related to the same exchange, it's just due to the spin-orbit coupling. So this is what you do to build your atomic configuration. That's essentially how this looks like when you write down in Hamiltonian. This is written in a particularly, let's say, explicit way that really tells you that you want to favor high spin and high angular momentum. Okay, so now I will describe the work which essentially uses theoretical methods like the dynamical mean field theory as sort of black boxes. You put all the interactions in and you see what happens. Then I will do some reverse engineering, so I will try to extract what's inside that, what is the physics behind, hoping also partially to answer to what Lara was asking about during the previous talks. So, essentially, what turns out is that if you do a microscopic calculation with all the details of the band structure, you include the Hubbard U and the Hund's J, you end up noticing that the level of correlation of this solution depends a lot on the value of the Hund's coupling J. This is the spin susceptibility, and this is the Sommerfeld coefficient, the prefactor of the linear term of the specific heat. Something which is associated essentially to the effective mass of the carriers. And you see this is something that increases a lot if you crank up the J interaction in a finite and reasonably small window of parameters. So it's very, very sensitive, while the same would not be for the Hubbard U. So this is an interesting observation. And actually, the other thing you learn is that if you play this game and you choose reasonable values of J and U, then you're able essentially to reproduce the effective masses of a variety of undoped iron-based superconductors, and also many features of the photoemission. So essentially it turns out that everything depends a lot on the Hund's coupling, and this dependence brings you to the right place. You reproduce what happens in the experiment. So the natural question is, of course, why? So now, before going back to the experiments, I will make you a small parenthesis of, say, theory of what the Hund's coupling does in a simple model. So the idea is that, and all this phenomenology I will describe now goes under the name of Hund's metals, essentially to contrast with the standard Hubbard's physics. So essentially so let's start from this. This is a cartoon of how the density of states of a hypothetical model material evolves if you crank up the interaction U. So you start from some blob with some density of states at the Fermi level, and then you see that this guy shrinks and shrinks. This is the effect of the correlation, this is the factor, the reduction, the quasi-particle weight, the reduction of the coherent part, and this thing, which is called usually Z, goes to 0. So the spectral weight disappears at the Fermi level, but it does by shrinking something which exists at the Fermi level. Of course, the spectral weight that goes away from here is moving towards high energy excitations, which are what we call the Hubbard bands. So this is the standard scenario for no Hund's coupling, single band Hubbard model standard thing. So the mode transition happens when this Z goes to 0, which also means that the effective mass is divergent. The guy is no longer metallic because the carriers are infinitely heavy. So what happens when you introduce the Hund's coupling? So say the black line would be this scenario here. So this is our Z, you increase U, and this guy goes more or less gently to 0. So you're, say, without particular scales, you're going to 0 at some value of U. And that's the Mott-Hubbard transition that, say, we know. When you introduce the Hund's coupling, what happens is essentially, if you see that first you have a very rapid decay. So you need a small U to make this guy reasonably correlated. And then you have a flat tail, where essentially this degree of correlation does not depend so much on you. So you clearly have a bichotomic behavior where that gives rise to a region where you can have, so, and the mode transition will happen eventually at some very, very large U. So what you will have is that you have a wide region where your system looks like is correlated. The features at the Fermi level are very narrow, but the mode transition is far, far away. This only happens when the number of electrons is different from the number of orbitals, as it happens for the nuclides. In the, say, more standard case of the half-filling, which is the one which is more favorable for a mode transition, this doesn't happen. You still have a one-phased thing, which actually drops very fast. Okay, so we're learning that there is, some stories, some things, interesting things happen. We can put them in a phase diagram. This is a phase diagram for simplicity for 3 orbitals. It's not yet the 5 orbitals of iron. And so these black things are where the system is a Mott insulator. So here, you sit here, you have 3 electrons, and the U larger than that, it's a Mott insulator. The same here, and so on. While the color scale here reflects the degree of correlation. Essentially, the whiter, the more correlated. So essentially what you have is that you see that the critical U here is small, that was the half-filling, while here it's large. So if you sit here, which would be the iron-based superconductors, it takes a very large U to have a Mott insulator, but still you have a large area of whiteness. Okay, that's what I was discussing before. What this graph wants to, so we are sitting here essentially. What the graph suggests is that actually this Mott state here might still be relevant to understand what happens here. So you should not think of the Mott state that it's very far at the same number of electrons you have. But you really should think that you're sitting at some doping from this other, much stronger Mott state. So let's see, so this is the, what we learned, say, before attacking the iron-based superconductors in this way. So now let's go back to our materials, and let's go back to the experiments to see if there is something at least reasonable in what I'm saying. So here, I will show you some collections of effective mass enhancement from experiments. So, this is done for the 122 family, for experts, which is the one which can be doped either with electrons, doping with cobalt, or replacing iron with cobalt, or with holes, replacing barium with potassium. So I'm putting everything on the same slide. So here there is, around here there is the antiferromagnetic spin density wave, and then there are 2 domes of superconductivity, but I'm just referring to measurements above the ordering temperatures and estimates for the effective mass. So the black dots here, which I joined with a black line, are from specific heat. And you clearly see that this thing doesn't care so much about what happens around the parent compound, but increases all the way down to here. So when I decrease the number of electrons, going from 6 to something less. Then this is the blue lines, is what is estimated from optics, or from optical measurements. And you see that the values are much smaller, but still you see a slight upturn. Then I show you also some more, so these of course are measurements that do not care about the different orbitals and different bands. You just measure one specific heat, one through the weight, one optical conductivity. So now I go with angular result for the emission and quantum oscillations. These are all measurements that instead are sensitive to the different pockets and different pieces of our fermiology. And you see that these guys spread. And essentially they spread more in the regions where there is a spread between the 2 original estimates. So essentially what I'm telling you here is that when you go in this direction, you have that effective mass increases, but it does in a very orbital selective way, or at least band selective way. There is a part of the electrons which gains a very large effective mass, the numbers like 9 that were mentioned before, and others that have a small enhancements like 2. So overall there is an enhancement, some average is enhanced, but it's very selective. So this is the, so, and what we learn also is that 6 here, the parent compound, is absolutely not special in this light. The effective mass doesn't care about that region. Okay, so that's the summary. Let me also mention sort of why we have this thing. Of course, if you now, so now we interpret all this in terms of a collection of, so we have many carriers with different effective masses. Essentially, in the specific heat, you have a sum of specific heats for the different carriers. So you sum up essentially the m stars. So the biggest one, if there is a spread, the biggest one is the one that matters. While in the optical conductivity, essentially the effective mass is in the denominator of any estimate of the Drude weight. So it's something that where the heavy guys matter. Also physically, you expect, of course, that in order to have real connection, you must wait for the slowest guys. So we have some, sorry, I'm messing up as usual. You have some, so the experiments are telling us that everything is selected. These are more direct experiments that I will very rapidly talk about. I mean, I'm not even talking about. There are measurements on these layered intercalated material where there is an orbital selective mode transition in photo emission. We see that the XY weight disappears at some temperature. This is essentially confirmed by terahertz spectroscopy, where you see that essentially you have clearly a signal which mirrors precisely the weight of the XY. That's in Joachim Deisenhofer's group. And there are also many evidences that tell you that you need to use a multiple fluid theory to understand what happens in all these kind of measurements. So there are evidences of orbital selective mod something, like axis for something, this transition or coexistence. Okay, so now let me go back in the final like 3 minutes to our theory. So our theory essentially here, I'll just show you, these are the parent compounds, and we get the same thing that I described before. So that was before for the model system, now is for the iron-based superconductors, and you see the two-step thing. First you go down very fast, and then you get something flat. So we are in that regime. So this is done in a realistic way. Not that it's really my fault, I guess. Wait, okay. And another important thing is that in this process, don't look at the details. These are spin-spin correlations. So the spin-spin correlations increase a lot while we go in this direction because the Hund's rule is dominating. And the Hund's rule wants the different orbitals to have the same, as much as possible, aligned spins. While at the same time, the density charge fluctuations between the different orbitals are frozen. Okay? So now let's go back to the main results. So now we just do our theory as a function, once again, of total doping. That's we analogous to the previous picture. That's 6. And this is the Z, the quasi-particle weight, the inverse of the effective mass. What you see is that all these guys go to 0. I mean, don't do anything special at 6. So once again, 6, the parent compounds are not Mott insulator whatsoever. But when you go in this direction, you approach an hypothetical material with 5 electrons, you would get the Mott transition. Okay? So this confirms what I was telling you before in model thing. Then one other thing is that I can play a nice game and plot the density of electrons per each orbital in the same process. So this is how many electrons we have for the different orbitals, once again as a function of the same variable. Okay, we get some numbers, because of course, I mean, the density is, I mean, the electrons can be wherever they, say, the chemistry tells they are. Of course, it evolves as a function of correlations. The nice thing is that we can plot this thing one as a function of the other. So now I'll plot this Z for an orbital as a function of the density for that orbital. So I neglect the total density, and then I have something like that, which tells you what? That, you know, here you see some things that go as some shape. Here you see that the Z of each band goes linear in the density of that orbital. So in each band, everything is controlled by the doping of that band. So this story of doping the Mott insulator comes back here. So you see that if you want to know if this material here, why a band is correlated or not, the answer is because the individual filling of the band is closer or farther from the Mott state. Okay, so this is really like a compass to understand a complex situation. So you have this whole bunch of M stars and numbers and everything, and this tells you why one M star is large and one is small. And it also connects strongly with the physics of ITC superconductors, because each orbital behaves now like an individual Mott insulator. And of course, that tells you that this hypothetical material with 5 electrons is our real parent compound, the one which is like the antiferromagnetic parent compounds of the cuprates. So now I can come to a final thing where this is the twist, is where I try to unify phase diagram of cuprates and peptides. So I just plot. This is the experimental phase diagram for the 1 to 2 as a function of what? Average orbital doping. So in my picture before, so it's essentially here, this would be 0 because we have 5. So this would be 6, which means 0.2. So it's 6 over 5 minus 1. And you see that if I play the simple game of joining together the two superconducting domes, I have one single superconducting dome right where the high TC superconducting dome is centered. What do I mean here? Is that, so now if you trust me for one moment on this thing, you have that the series of phases that I obtain here is exactly the one that I described in the previous slide. You have the antiferromagnetic MOT in this putative material with 5 electrons, if I would dope with many, many more holes than potassium. A selective MOT state, a one in which the orbitals are very, very much different one from the other, which is the version of the pseudo-gap region here. I don't think I have time to discuss this. Then there will be the superconductor, and finally the normal metal. So clearly here, the idea is that here at 6, in reality, there is of course the spin density wave, but this is more like an accident. It's a situation where you have nesting, or you have a lucky situation in terms of number of electrons that can form a sort of spurious spin density wave which overtakes over the superconductors. But still, the overall shape and everything, and the way you should look at the phase diagram, remains the one of the cuprates. Okay, this is just to tell you that actually if you do some DMFT-like calculations for the cuprates, you actually get that the pseudo-gap region looks pretty much like our selective phase. Because essentially it's a region where the antinodes behave like essentially MOT localized electrons, while the nodes keep their Fermi liquid nature all the way down to very, very low underdoping. So the link between the missing link, if you want, between the pseudo-gap and this orbital selectivity is established at least within this kind of calculation. I skipped this new thing and okay, the conclusions are essentially what I just said. Hund's rule is crucial, it changes the role of correlations. The important MOT state is just the one at 5, you should not look at 6. The parent compounds are irrelevant in this side. If you do that, then you realize that everything is just like a collection of single band MOT insulator, and then you can unify some apparently different phase diagrams. Thank you.
I had a question which I think comes rather natural after this final phase diagram you drew, which is this. Does this scenario cast at least a shade of doubt about the role of spin fluctuation as mediators of pairing? Would you rather be inclined to say that there is more like a MOT physics?
Yes, I mean, let's say, I can take a light or let's say a strong version of the scenario. I mean, take the one where all this story is just what, say, prepares the ground for any pairing mechanism. So the pairing mechanism might as well come from spin fluctuations, which are a little more than the accident I described before. But still, this would be important because it tells you that, the ground where superconductivity comes from is important as well. Or I can take, a more extreme point of view and question the spin fluctuation scenario in this light. Thinking of a more, this is something we are working on. Actually, it's very complicated in this case because even though you have a compass to disentangle the thing, still,
The way you put is that spin density wave compete with superconductivity.
The static, the actual magnetic spin that wave does. It's still possible. Frankly speaking, I don't think it's the case. But I would not say that what I presented does not rule out spin fluctuation. Of course, serious.
I say casts a shade of
yeah, sure. I went a little farther, but
because in a sense you should attack the question what is the super. He didn't calculate explicitly superconductivity, so until that you don't give a scenario for the superconductivity, but
yeah, sure.
All the rest is
and it's something we are working on. We are essentially exploring the scenario where, of course, it's the MOTness from 5, which, by the way, doesn't mean that it's not bosons at the end of the day. Coming back to Lara's question before. So even in a scenario where it's just MOT physics, at the end of the day, at least in the overdoped region, you can always build up some effective bosons. I mean, and it comes out from a DMFT calculation. So let's say, I mean, at least in the, say, the black box part of this, we can answer to that. And of course, I hope also to go back to the, what I like to call reverse engineering, to understand what's in the black box, of course, open the box.
Okay.
So I wanted to ask the same question about what does it make for the superconductivity. Of course, what you answered that, and I like this phase diagram a lot, that exactly this SDW phase is really sort of accidental, and we know from the materials that it's in 1 to 2 it's the case, but this is exactly where the nesting occurs.
Yeah.
And in 111 there is nothing like that. In iron selenium there is no magnetic transition. So this.
Yeah, no, I want to be extremely, say, pedantic, but, but I agree.